Okay, we can start. So today I'm going to show you an example of solving the kinematics of a mechanism using the graphical method, and in the next video using also the analytical method. So first of all, this is the example. The example is chosen because I understand that all of the examples in the book, as well as in the video, in the lectures, have rotational motion as a input motion. Here, in this example, the input is a translational motion, and such example is not solved in the materials, in the lecture materials, I understand. Okay, so we can, first of all, we have this kind of the mechanism. What is known? So first of all, the velocity of a link 1 is known, and this is a function of time. I changed this example because I wanted to have also the non-zero acceleration of this first link. So we know the v1, a1 of course, and entire geometry. Our task is to compute the velocity and the acceleration of a point D as output motion. So first of all, I wanted to talk about something, the displacement analysis. It is not done in the materials, but as you can see, before we analyze velocity and acceleration, we should also know about the range of motion. So for example, we should draw this mechanism for two extremal positions of the driving link. So for example, for two values of this displacement S1, and we should see what is the corresponding angular displacement of a point D. For example, we need to know this because we want to have some range of motion of the mechanism, and maybe our geometry of the mechanism is incorrect, and we cannot obtain this desired range of motion. So we have to check what is the range of motion of the point D, and then maybe if we need, we have to change the angles or length of the links of the mechanism. So first of all, remember that in the design step you should think about the range of motion, and if the range of motion is not as you wanted, you can always change the geometry, the distances between points, and so on. But let's go to the graphical method of velocity and acceleration analysis. Okay, so here we have our first task. We need to compute the velocity of a point D. We cannot start with the point D because there is not enough data to compute this displacement, but we should start with points which are known, which velocities are known by us. So for example, in this case, the point D is such a point. The point D is a point which belongs to three, let's say, in the point D, three links coincide with each other. So there is a point B1, let's say, belonging to the point to the link 1. There is a point B2 belonging to the slider 2, and the point B3 which belongs to the rotating rod 3. So we can and because these points coincide with each other, we can tell something about the motion and about the velocities of this point. So we look at the mechanism, and we see that there is a rotation of a rod 3, and okay, maybe in some other way. So we look at the mechanism. So we see that the velocity of a point B, okay, maybe we'll talk about the motion. So we have the point B, and what is the motion of a point B with respect to the fixed point, some point 0, let's say, or point C, which is fixed. We see that this motion is a complex motion which corresponds with the rotation of a rod free, and there is a relative motion of a slider 2 with respect to the rod free. So the resulting motion of a point B is a sum of two motions. First, the motion, the rotation of the rod free, and the translation of a slider 2 with respect to the rod free. Therefore, the velocity of a point B will be the velocity which is a sum of two. So, velocity of a point B, in our equation it is called VB1, is equal to VB free, which is the velocity due to the rotation of a rod free, plus VB2B free, which is a relative velocity of a point of a slider 2 with respect to the rod free. And these two velocities will give us our absolute velocity VB1. When we look at the mechanism, we also see that we know the VB1. Why? Because the point B belonging to the rod 1 is fixed to the point A. This rod 1 is fixed, is welded to the slider, and there cannot be any relative motion between B and A. So the VB, this absolute velocity with respect to the fixed frame, must be equal to VA, and therefore we have our first equation. So the velocity of a point B with respect to fixed frame is equal to VA, which is known by us because this is our data, but this velocity is also a sum of two velocities, VB free, which comes from the rotation of a rod free, plus VB2B free, which is a relative velocity of a slider with respect to the rod free. Therefore we can write this equation. And when we look at this equation, we can start solve this equation by vector graphs. So we start with drawing the VA, VB1, because it is given to us. And what is else known? We don't know the values of the velocities VB, V2, B3, or we don't know the VB3, but we know the directions of these velocities. First of all, in case of the VB3, the direction of velocity must be perpendicular to the rod BC, because this is velocity due to the rotation, and you know that in case of the rotation, the velocity is always tangent to the path, to the circle of rotation. And also we know that VB2B3 must be along the rod BC, must be parallel to the rod BC, because it's a relative motion of a 2 with respect to the slider, and it only can move in one direction. So we can draw the directions of VB3 perpendicular to BC, and VB2 B3, which is parallel to BC, and after that we have to find the point of intersection of these two directions. And having the point of intersection, we can proceed with drawing the entire vector polygon. So we can draw this, and this is done in the slide. So we see that VB3 plus VB2B3 must give VA. And of course, having drawn these vectors, we know the unknown velocities. But our task was to find the velocity of a point D. So first of all, we see that the rod free points BCD are connected by a weld. They are fixed together, so they can if the rod free rotates, also the point D rotates with the same angular velocity. So there is one angular velocity for point B and point D. So we can compute this angular velocity. It is VB free divided by BC, where BC is distance between point B and C. And having the omega free, we can now compute very easily VD, because this is just a rotational motion. So VD is equal omega free times CD, the distance between point D and C. And for the sake of completeness, I'll also computed the velocity of a point S free, which is also computed because this is also the same rigid body, and S free also rotates with a velocity, angular velocity omega free. In the next step, we have to compute the accelerations. And of course, we use exactly the same idea as in the previous case. So first we analyze the acceleration of point B, and we see that this acceleration comes from the rotation of a rod free, as well as a relative motion of a slider 2 in a rotating frame of reference of a rod free. So as before, the absolute velocity of a point B, absolute acceleration of a point B must be equal to the acceleration of a point A, because the rod BA is fixed, and there cannot be any changes in acceleration between these points. So we see that AB1, the resultant absolute acceleration, is equal to AB free plus AB2B free plus AB2B free Coriolis. Why? First of all, AB free is the acceleration of a point B, which comes from the rotation of a rod free. AB2B free is acceleration of a slider in a relative motion with respect to the rod free. And of course, we have a case when there is a rotating frame of reference and a relative motion in this frame of reference, and therefore there has to be also a Coriolis acceleration, AB2B free Coriolis. So now we can start to see which accelerations are known to us. So first of all, AB free, we don't know neither direction nor the value, because we cannot assume that the epsilon free is equal to 0. It is not, probably, and we have to assume that AB free has two components. AB free has to be decomposed into two components. The first is AB free normal. It is the centripetal acceleration of a point B with respect to the point C in a rotation of a rod R, and AB free T is the tangential acceleration. So we have two perpendicular components of accelerations. First is centripetal, normal component of acceleration, and the second is tangential. First is due to the rotation, just due to the omega free, and the second component is due to the non-zero epsilon free. AB2B free is, we know the direction of this acceleration because our rod is a straight line. If the motion of a relative motion of a slider was curvilinear, then we had to also include the normal part of acceleration. But in our case, this is a straight line motion, so we have only AB to be free one component. And there is also, of course, Coriolis, as I told before. Now we are looking what we know about this acceleration. So let's first look at the AB free normal. AB free normal is the centripetal acceleration in this computation. It can be computed omega free square times BC. We know omega free, so we know this both the direction centripetal as well as the magnitude which is given by this equation. Also, we know both the direction and the magnitude of a Coriolis acceleration. First of all, direction is given to us because we know that the Coriolis acceleration is a vector sum of omega and VB to be free vectors, and therefore it must be perpendicular both to the omega and to the VB to be free, and these three vectors must form a right-handed coordinate system, and therefore we can find the direction of the Coriolis acceleration. Also, we know that the value is the value of the which also comes from the vector sum vector product. Sorry, I thought vector sum vector product. So it's omega free 2 omega free times VB to be free, because this is given to us by a vector product, and direction is also given to us by a vector product 2 omega free cross VB to be free, and the vectors v omega free, VB to be free, and Coriolis acceleration vector must form a right-handed coordinate frame. Therefore we know the direction due to the vector product and due to the values which are given to us, because omega free and VB to be free has already been computed. So we can start drawing our vector diagram. So we start with AB1. AB1 is equal to AA, and this is given to us, so the resulting vector is known, and we have to start with the end from the end of this vector to draw the vector sum. So first we draw all of the vectors which are known to us. So AB3 normal, which is known, so we can draw this vector, and also the Coriolis acceleration is known to us because we have the magnitude as well as the direction, so A Coriolis, B to B3 have to be drawn first. And there are two more vectors which are known to us only their direction is known to us, yeah, because AB3 tangential, we know the direction, it must be tangential to the rod BC, which moves in a rotational motion, and of course we know the direction of AB2 B3 because this must be along the rod BC. It is the acceleration in relative motion of a slider 2 with respect to the rod BC. So we have to draw two directions. The first is parallel to the BC, and the second is the perpendicular to BC. So we start, we draw first direction from the end of the Coriolis vector, and the second must be drawn from this AA vector because this vector must add up to form a sum of the vectors. So if we have these two directions, we can now find the point of intersection of these directions, and we can draw our missing vectors. So in the final vector diagram we have found the two unknown vectors AB to be free and AB free tangential. So it ends our analysis of the acceleration of a point B. As before, the real goal was to find the acceleration of a point D. So first of all we have to compute the angular acceleration. Angular acceleration is given to us as AB free tangential divided by BC, where BC is the distance between point B and C. And having known the angular acceleration, we need to compute two components of the acceleration of the point D. First is the normal component, and the second is the tangential component. So the normal component is equal to omega free squared times CD, and the tangential component is equal to epsilon free times CD. So we have the values of these components, and we also know the directions, because one of them, normal, must be centripetal, so it must be along DC, and the second component is tangential, so it has to be perpendicular to the rod DC. So having values and directions, we can find AD as a vector sum of AD normal and AD tangential. And of course we must do exactly the same computation for an acceleration of point S3. Why do we need S3? Because as you see on the graphics, this S3 is the center of mass of the object, and this is the point where the inertia force will be acting, and therefore we need to find the value of the acceleration at this given point. Okay, I think I can now finish this movie, and then the next movie we'll talk about the analytical method of kinematic analysis.